If you think it is leaking, please raise your hand. If you think it is lagging, please raise your hand. So I ask again. If the output is a motor, do you think the motor current lead or lag motor voltage? If you have a motor, do you think the current is lagging or leading? If you think it is leading, please raise your hand. If you think it is lagging, please raise your hand. It should be lagging, right? Because inductance, so you have V, you have Z. Then this is I, so I is lag theta, right? So you have voltage here, you have inductor, so the current should be lag. So the output is lag. You can see the output. Voltage is 0, but the current minus side, which means current, the output current, lag output voltage. So it is lagging. If output is lagging, how about input? So you can compute this equation. So II1 is T1, T sequence multiplied by IO1 plus T3, T sequence multiplied by IO2 plus T2, T sequence multiplied by IO3. So finally you found input current is leading or lagging. Also lagging, right? Output is lagging 37 degrees. How about input? Input is 220. It is 60 Hertz. Then it is also lagging. Output is lagging. Input is lagging. Do you like input lagging? No. You hope power factor correction. So what do you need? Unity power factor, right? So what do you need? You hope the current should come here, right? Then what can you do? You say, I design a power factor correction circuit, but it is too expensive, right? So what I want to do is, can I change the switching function? And then I can improve the input current, become unity power factor. Yes or no? Can I do this? If you think yes, please raise your hand. If you think no, please raise your hand. Can I change the switching function to make the input current become unity power factor? Possible or impossible? If you think possible, please raise your hand. If you think impossible, please raise your hand. Which way? Possible or impossible? If your advisor say this can become your PhD dissertation, you improve the power factor, become unity power factor. Do you like to do this? Yes. So it is possible. But how can we do this? So we can improve power factor, just change the switching function. So the answer is how to get unity power factor. So the answer is quite simple. It is like this. So I will explain here. We have this one. We have this one. So we have V in 1, V in 2, V in 3. So we have input voltage here. This is B phase. This is C phase. So we have T1, T2, T3. So this is IO1. This is IO2. This is IO3. We have three-phase current. And we have T1, T2, T3. How about the next one? Did you remember? T1 should move here. T2 should move here, T3 should move here, right? Shift 120 degrees. How about next one? T1 should move here, T2 should be here, T3 should be here. So this is the switching function. But now I want to change. If I do this, then what happens? The input is here, V in 1, but the current is here, I in 1. So this is I in 1. Then I know it is lagging, not good. I need unity power factor. So how can I improve the unity power factor? Then I think T1, T2, T3, like T1, T2, T3. But here, I want to reverse, right? Change the current to become heating. So I need to reverse. How can I reverse? So I switch these two. So this become back. Original T3, T1, T2. I change this to here. I change this to here. So this is T2, T3, T1, right? And I move this to here. T3, T1, T2. So original could be this way, but now I go this way, right? Then in average become 0. So I move forward, another I move back, then become 0. So the idea is like this. So we have two stages. In stage 1, T1, T2, T3, T3, T1, T2, T2, T3, T1. In stage 2, T1, T2, T3, T2, T3, T1, T3, T1, T2. So we change the sequence. So V in 1, V in 2, V in 3. Then we change this to the second. We switch this one. We switch this one. Then we can get one is lagging, another is leading. Then we have two stages. We have sequential 1 and the sequential 2. Then finally, we can get unity power factor. So this is T1, T2, T3, and then T2, T3, T1, and then the third one is T3, T2, T3, T1. And then the second is T1, T2, T3, T2, T3, T1, T3, T1, T2. So one sequence 1, another second 2. This is 1 millisecond. This is another millisecond. The whole period becomes 2 milliseconds. So we rotate. So the first step I go forward. The second step I go back. Then it becomes 0. So they use this idea. Then the student get a PhD and they get a patent and they get a job. So the idea is very good, right? I can change the switching pattern. Then I can get unity power factor. So I have a free lunch. I don't need to design circuit. So we call this one AC to AC. But this is AC to DC and DC to AC. So how many stages? 1 stage, another 1 stage, 2 stages. What is the advantage? If I have some problem, because this is a huge capacitor, the capacitor can keep constant voltage. Is this good or bad? This is good. We have storage here. Where is capacitor? No. If you have no capacitor, then if you have some problem, then the energy cannot balance. So how about the PWM? Input is DC, output is AC. Then you can develop the PWM easily. Here, input is AC, output is AC. How about your PWM? Very hard, right? You have no idea what can I do. But here it is clear. I change AC to DC. Then I change DC to AC. Then the technology is very good. And I can use it. How about a power factor? Which one power factor is better? Here, what is your voltage? Your voltage is here. How about your current? Your current is here. Do you think that the power factor is good? Not good. You need a PFC. How about this one? You have switching 1, switching 2, then unity power factor. How about the energy regeneration? If I want to recover the energy, then I can have energy to the DC bus. Then I want to move the DC energy into grid, but we have diode. Can I go back? No. But here, I can, from input power to output power, we can regenerate, we can recover output power into input. So this is better. We call this is energy recovery and the unity power factor and the high quality. But this one, the PFC power factor is bad, harmonics is huge. So how about a device? Which one is cheaper? How many devices do you use? 1, 2, 1, 2, 1, 2, 6 dial, 6 switch. How about this one? You say 9 switch, 9 AC switch. So which one is better? 9 AC or 6 dial plus 6 IGBT? Which one is better? If you think this is better, please raise your hand. If you think this is better, please raise your hand. Which one has low switch, cheaper switch? This one or this one? So what is AC switch? If you have IGBT, you go here, this is not AC switch. If you need AC switch, then you have to use 2 switch parallel. Go here, go here. So this is equal to 1 AC switch. So 1 AC switch equal to 2 DC switch. If you have 9 AC switch, how many IGBT do you need? 18. Here is 6. Do you think a diode is better than IGBT? Cheaper, right? So this is cheaper. Originally you think 9 AC, only 9 switch, but 9 AC is 18 switch. So this one has low switch than this. However, it need a huge capacitor. Do you like huge capacitor? So you have a circuit. You have a circuit here. The capacitor is here. Your circuit is here. Do you like this? No. It is huge. And how about the life of capacitor? 5 years. After 5 years, you have to replace the capacitor. And the capacitor is very tall. And the volume is very huge. But if I use the silicon base, then it is small. So this one is smaller than this. So we have small volume, we have high efficiency, we have more device. So we can compare this one. So we call this is indirect switching method, or we call this is AC to DC and then DC to AC. But if we have AC switch, we can think we have AC input. But first, we convert to DC. And then we use DC to AC. But this is in our own brain. The physical is AC to AC. But we can think AC can convert to DC. And then DC convert to AC. Because it is easier for our brain, right? Otherwise, it is too complicated. So we can think this is AC to DC, so AC to DC rectifier. And then DC to AC, so we have inverter DC to AC. Then we can develop the switching function. So we can combine AC to DC and DC to AC, and we can synthesize the real AC switch. So we will discuss later. So we have another modulation method. So how many patterns do we have? So this is direct switch. Direct switch, how many switch? So we have 1, 2, 3, 4, 5, 6. So the switching table only 6. So we have a very brief summary. In this chapter, we discuss about AC to AC cycle converter. What is cycle converter? We use SCR to obtain AC to AC, but we need a 36 SCR. The circuit is too complicated, and we discussed this is too old. No people want to use it. Too complicated. Harmonics is too huge, and the output frequency should be lower than input frequency. So now we prefer matrix converter. So matrix converter need AC switch. What is AC switch? Bidirectional switch. What is bidirectional switch? Two direction. You can go up, you can go down. So it is AC switch. And we will discuss the details of the matrix converter. Now we only give you a fundamental concept, but how can we implement the matrix converter? We will discuss later. So this is this chapter. Then we will move to the we call PPT about the real matrix converter. So now we discuss about the real matrix converter. So you can say, I want to use matrix converter for my PhD. It is okay, because this is a new field and a lot of challenge. So you can say, introduction to matrix converter technology. It is not a concept, it is a new technology. So about its power electronics, about the motors and the control. Okay, so we will discuss, focus on the matrix converter. So what is matrix converter? So first, we will introduce the basic principle of matrix converter. And how can we implement it? How can we do the PWM modulation, design the filter, and decide the loss and the real applications? So matrix converter is a new technology. It is not a concept, it is a technology. So what is matrix converter? We need 1, 2, 3, 4, 5, 6, 7, 8, 9 AC switch. So we call this AC switch or bidirectional switch. And then we can drive motor, but it is AC to AC. So input 60 Hertz, output from 0 Hertz to 120 Hertz. So we can push the output frequency higher or lower than the input frequency. However, if we use a switch, then we create harmonics. So we still need LC filter. So small L, small c. So if we compare to the AC, DC, DC, AC, they use a huge DC link capacitor, very huge. But here, the capacitor is very small. Okay, so this is the difference. One is a small capacitor, another is huge capacitor. So basic ideas. What is matrix converter? So first, we have to avoid input A phase and B phase short circuit. So if you put this switch on, then you short circuit input voltage. So you have to avoid input voltage short circuit. You have to avoid output open. So what is output open? If I open this switch, and open this switch, I open this switch, open this switch, open this switch. Then we have no path. Then we have 10 ampere here. The 10 ampere becomes 0 ampere. Then we open the output, right? So it is not allowed because output should be constant current. So we cannot open the output current. So each output phase should connect to input phase. So we can have this one on, or this one on, or this one on, then we can have the current. But if none of the switch on, then we open the output. If more than two or three, then short circuit. Switch duty cycle, we can modulate, we can decide the turn on duty cycle so that the average output voltage can follow the ideal output voltage. Then we can get 30 Hertz output voltage. And the modulation is arranged so that we use the average ideal. Average input current is sinusoidal, and the average output voltage is sinusoidal. So we use the idea of average. So if you study matrix converter, you use capital A, B, C. What does this mean? Means input. So capital A, capital B, capital C, this means input. So we always say VA, VB, VC. Capital A, B, C means input. For output, VA, VB, VC. We use small ABC to represent output. So this is traditional. Otherwise, people get confused. So you have to use capital A, capital B, capital C to show input. Small a, small b, small c to show output. If you say AA, what does this mean? Means the switch connect input A and output A. So AA. Okay. So this is the fundamental label. People always use this label to show the matrix converter. So we have to decide T1, T2, T3. So we have T1, T2, T3, then T1, T2, T3, then T1, T2, T3, T1, T2, T3, then T1, T2, T3. So we have, and then we have T sequence. So T1 plus T2 plus T3 is T sequence. In general, T sequence is 1 millisecond. If this is 1 millisecond, what is the switching frequency? 1 kilohertz. So the switching is quite low, only 1 kilohertz, not 10 kilohertz. So this is the matrix converter. Why don't we push 10 kilohertz? Because the computation is too long. We need a lot of computation. So what is the voltage? So you can see the output voltage like this. So this is fine. This is line to neutral phase voltage. If you see this voltage, can you tell me what is the frequency? Can you show me what is the output frequency? The answer is 25 Hertz. But it is very complicated, right? If you change to line voltage, it is more clear. It is like this. So you can see this is line to line voltage here. So you can see 10 milliseconds, this is 20 milliseconds. Okay, so we call this is line voltage. Line voltage is very close to square waveform. Square waveform. Okay, this is 50 hertz. Output is 100 hertz. So like this. So for our eyes, it is very hard to see what is the output frequency. The answer is 100 kilohertz. How about the output line to line? It is like this. It is like this. So for one cycle, what is one cycle? 10 milliseconds. The inverse of 10 milliseconds is 100 hertz, right? So this is output 100 hertz because one period is 10 milliseconds. So if you have 10 milliseconds, then it is 100 hertz. So output is 100 hertz. So we can see the output voltage, line to line voltage. Okay, so this is 50 hertz to 25 hertz. So you can see this is 25 hertz. So for the time interval, it is 40 milliseconds. So you can see for a circle, it is 40 milliseconds. And this is input current. Input current is like this. So you can see input current is like this. So it is quite close to sinusoid. If you use the inverter, it is like this. So use AC to DC, it is like this. The current waveform is not good. But now I use the matrix converter. The current waveform is better. It is very close to sinusoid waveform. So this is the frequency domain. So input is 50 hertz, output is 25 hertz. So this is 2 kilohertz switching. So we can see the harmonics is near 2 kilohertz, then 4 kilohertz. So we call this is sideband, 2 kilohertz, 4 kilohertz. This is the fundamental. The input is 50 hertz. The output is 25 hertz. So very clear. Modulation control. How can we decide when should we turn on, when should we turn off? So continuous control of output voltage amplitude. So output voltage can from 0 to maximum. And the output frequency can from 0 to how many? To the 10% of switching frequency. What is switching frequency? 1 millisecond. 1 millisecond inverse is what? 1 kilohertz, right? Now the output frequency maximum is 10% of 1 kilohertz. What is 10% of 1 kilohertz? 100 hertz. So you can see your PS switching frequency 1 millisecond. Then your switching frequency 1 kilohertz, 1000 hertz. But now you have 10% of 1000 hertz, which means your output maximum is 100 hertz. 100 hertz. In general, matrix converter maximum frequency 100 hertz. How about the minimum frequency? 0 hertz. You can change from 0 hertz to 100 hertz. What is the advantage? Unity power factor. You can achieve unity power factor. Only change the switching frequency. No circuit, no extra circuit. If you design AC to DC and then DC to AC, then you need a huge capacitor. So this one, we use AC to AC, we do not use any capacitor. So what is the future of the matrix converter? We do not need any DC link. So no DC link capacitor. If you do not use DC link capacitor, which means your size becomes small, right? Because DC link is very huge. So if you have a circuit, the DC link like this, and the other is your IGBT. So it occupies this area. But now I can remove DC link, which means I can reduce space. So no DC link. So all devices are silicon device. Silicon device is small, so we call this is silicon-based solution. So we can put the whole circuit in a small size. No restriction on input. So input could be 220 or probably 60 Hz or 50 Hz. How about output frequency? From 0 to 100 Hz. So we can change from 0 to 100 Hz. Very huge, very huge. So we can have bidirectional power flow. The power can come from input to output or output go back to input. We have bidirectional power flow. We have 4 quadratic. We can use as motor or generator. We can use motor and a brake, generator and a brake. We call this 4 quadratic voltage current characteristic. We have sinusoidal output current. We have sinusoidal input current. Input and output current are sinusoidal. But if you use traditional inverter, then input current is not sinusoidal. It is pulse. So this is not good. If you need a sinusoidal current, you have to design PFC. It is very hard to design. So now we can obtain sinusoidal input current, sinusoidal output current. This is the advantage. Potential for high power density. So if switching frequency is high enough, so we can have a very high power density. What is high power density? Small size but create a lot of power. So do you like this? Small size, huge power? Yes, high power density. Output voltage limit is only 87% of input. This is the disadvantage. For the traditional, what is the DC voltage? If you have voltage here, then you can have DC here. DC is peak, right? Peak. But if you use matrix converter, the output voltage is maximized 87%. So if you have 220, then peak value is this one, then you have to multiply by 87%, which means your DC bus is lower. You cannot reach peak value. Why? Because you don't use capacitor. So your DC voltage should be reduced. This is the disadvantage of matrix converter. So how many power devices should we use? 18. So it needs more semiconductor. It is 9 AC switch, but 18 IGBT. So if we do not use matrix converter, what can we use? We use traditional inverter. So AC rectified to DC, DC to AC. So this is traditional inverter. What is traditional inverter? We call it is workhorse. What is workhorse? The horse always work in the field. Which means the horse is reliable, right? And useful. So if you go to industry, everybody uses this. Nobody uses this because this is workhorse. If it's not good, but it is cheap, reliable, so everybody use this. The AC to DC and the DC to AC inverter can come from kilowatt to megawatt. So if you go to MRT, if you go to high-speed train, everybody use it. So it is workhorse. If you go to field, you see a lot of horse. The horse can work different jobs. So now people use this circuit to design inverter. However, there are several disadvantages. Unidirectional power flow. The power go here, go to motor. But if motor wants to regenerate the power, it can come here, but it cannot go to grid. Then you cannot save energy, right? So this is not good because we need to save energy. If you have high-speed train or MRT, when they go to the station, they need to reverse the energy to Taipower company. If you have elevator, then the elevator goes down. It can generate energy to power company. Then the power company should pay money to the user. So because I regenerate energy to Taipower company, so every year Taipower company should give me money because I provide energy to Taipower company. So, but now you cannot reverse. So how about your energy? When you break, you have to put a huge resistance here to dissipate your energy. Otherwise, the voltage becomes too high. So you use a huge capacitor to waste your energy. Do you like to use resistance to kill or to dissipate your energy? Do you like to do this? No. So do you like to recycle, or do you like to put every garbage into the waste way? You need to recycle, right? So now we also need to recycle, but we can't because our energy cannot go back. So this is not good. Poor current like this. If you need a good power factor, you have to pay. You have to replace the diode into IGBT. Then the cost becomes twice, right? We discussed this before. So DC link capacitor often 30% or 50% of the volume. So if you open the case, most of the volume is occupied by the DC link capacitor. And the life is only 5 years. So you have to replace the DC link capacitor. So the inverter has some disadvantage. So what can we do? You say, I can improve power factor. How can I improve power factor? I use IGBT. So if I use huge capacitor here, I use 6 IGBT here, 6 IGBT here, then this is for inverter, this is for PFC, right? Then I can improve the PFC, so bidirectional power flow. So I can use the IGBT to convert the DC energy into AC energy. So I can do the regeneration. So it is good, but it is too expensive. So your price becomes double. And the theta phase control can be done here. So we can do the power factor from this circuit, and we can do the inverter from this circuit. And we need a huge capacitor. And the volume becomes very large. So we need an inductor here. But AC to AC, then we have bidirectional energy flow. We have unity power factor. Then this is equal to this. The function is equal, but the circuit is different, right? We can use this circuit. We can use this circuit. What is the disadvantage of this circuit? We need a huge capacitor. Here, no capacitor. Here, we need 6 IGBT for inverter, 6 IGBT for PFC. But this for PFC is too expensive because we say PFC should be a free lunch. But now you pay half for the power factor correction. It is too expensive. But for AC to AC, we only change the switching pattern. We do not need any hardware. So this is the difference. So if you want to study PhD, then it is good to compare back to back and matrix converter. Which one is better? So for the matrix converter, we have some disadvantage, voltage transfer ratio. So the DC voltage only reach 86%, which means the output voltage is reduced. And we have 80 IGBT, 9 AC switch, 80 IGBT. But for the previous one, PFC plus inverter, we only use 12 IGBT for back-to-back, right? So back-to-back only 12, but matrix converter 80, more than back-to-back. Control everything. We like DC because DC is easy to think. We don't like AC to AC. It is too complicated. So we prefer DC to AC, not AC to AC. And then we have to rely on DSP to compute T1, T2, T3. It is quite complicated. So we rely on DSP very much. So we call it is intensive. So DSP becomes important. If the DSP is too slow, then your performance becomes worse. So you need to rely on high-speed DSP. But now DSP become faster and faster, so it is not an issue. It is not an issue right now. So this topic is quite serious. We have to compare in deep. Matrix converter, 80 IGBT. Back-to-back, 12. But back-to-back need one huge capacitor. So do you think one huge capacitor and the 6 IGBT, which one is more expensive? It is very hard to say, right? And this is huge, but the 6 IGBT is small. Okay. And for inverter and diode, we need 6 diode and 6 IGBT. But the problem is we need a huge capacitor. And the input current is not good. It is like this. And we cannot do regeneration, right? If we need a good performance, then we have to do back-to-back. If we do back-to-back, it is too expensive, right? So it is very hard to decide. Which one do you prefer? Do you like this one? Or do you like this one? Or do you like this one? So if I set a rule, your input current should be sinusoidal, then you cannot use this, right? The only two choices is this. You can use this or use this. But here, you need to buy a huge capacitor. Here, no capacitor. So they have advantage and a disadvantage. So for conventional rectified DC link inverter has poor input current. And we cannot do regeneration. So the energy cannot go back because the diode will block the energy. We need a huge DC link capacitor. For the back-to-back inverter, we can generation function. We can have sinusoidal input current, but we also need a DC link capacitor. For the matrix converter, we can have regeneration ability. We can have sinusoidal input current, but we do not need any DC link capacitor. But we need 18 devices. So each one has an advantage and a disadvantage. No one is the only choice, right? So people can choose different way to reach their goals. So technical challenge. So if you want to study matrix converter, what is your challenge? First is no free-filling type. So before, if we design the matrix converter, then we can say we have a diode parallel with the device. So we always provide a phase pad here, right? So if this turn on, it is okay. But if the current goes this way, we can go the diode, right? So we call this free-wheeling diode. So if you have that low, that type, then this turn off, then we can go back to here to avoid the spike, right? So this is good thing. But if you have AC switch, can you put a diode here? No. So you have no free-filling diode. No free-filling diode. Then if you turn off, if the switch turn off, and then you have inductor current here, but you have no diode, then it creates a spike, then damage your device, right? So you have no free-filling diode. This is a disadvantage when you have that time. And we have to design current commutation. We will discuss later. What is current commutation? If you have current here, 10 ampere, original this one turn on, then this one turn on. If this one not turn off, this one turn on, then short circuit, right? If this one already turn off, this one not turn on yet, then open circuit. Now you need keep 10 ampere. You need to avoid short circuit. What can you do? No way, right? No way. Because you cannot jump immediately. So if you have overlap, then short circuit. If you have dead time, then open circuit. So this is challenge. Current commutation. Circuit protection. So before you have snubber, you can put snubber here. You say, I want to protect my device. So what can I do? I put snubber. If I turn off, then I can charge the capacitor. Then capacitor can go here. Then original I have spike, but now I can remove the spike by using the snubber. But now you have AC switch. Can you design this one for AC switch? No. So you have no snubber. No snubber. So this is challenge. No snubber. So if you short circuit, how can you protect? Just burn out. So short circuit protect. How about open circuit protect? If the switch, if the DSP fail, then DSP make the switch on. Then this switch turn on, this switch turn on, and short circuit. Because DSP sometimes turn on the switch, sometimes turn off the switch. But in some case, if DSP do not provide any signal, it is turned on, then short circuit. So you have controller function protection. So what is the application of the matrix converter? It is designed to meet specific application need. So some special case. And Yaskawa, they put a lot of efforts for matrix converter. And then they provide a real product in the market. And it can show this product is better than imported. Small size, low cost, high efficiency. But you need technology. So some companies already developed this product. So can you choose matrix converter as your PhD? The answer is yes. So now we go to the power circuit implementation. So how can you design your bidirectional switch? So we need an AC switch, so bidirectional switch. So how can we do this? We need to do current commutation. How can we do the current commutation? And we have many ways. We have to consider layout, because it is high power. And we have to consider the loss and the protection. So a lot of practical issue. Okay. So what is matrix converter? We have 9 switches, but we should provide bidirectional switch. What is bidirectional switch? Means the current can go this way or the current can go this way. Bidirectional. Means the voltage could be plus minus or plus minus. So they have bidirectional ability. So it could be positive or negative current. It could be positive or negative voltage. But for traditional IGBT, they only go in one direction, go this way. They cannot go this way. So we call this is unidirectional switch. Unidirectional switch. But now we need a bidirectional switch. 2-directional. Bi means 2. So we need 2-directional switch. So how can we design 2-directional switch? You can use this idea. So I can go this way, go diode, go IGBT, go diode. I can go this way, go diode, go IGBT, go diode. So the current can go this way or this way, right? Do you like it? Yes. Why? I only use one IGBT. Here we need 2 IGBT. Here only 1 IGBT. But you also need 4 diodes. So each diode has diode voltage drop. So this could be 2 volt, 2 volt become 4 volt. So you have more voltage drop than this one. This one only 1 IGBT drop. But this one, 1 IGBT plus 2 diodes. So you can see 1 IGBT voltage drop plus 2 diode voltage drop. 1 diode 2 volt, 2 diode 4 volt. So it creates loss. So this is conduction loss. So you need high conduction loss. But you only use 1 switch. So the circuit is cheap because diode is cheap. But the loss is higher because when you turn on, then you have 2 diodes plus 1 IGBT. And do you think that the circuit is large or small? Because diode is huge. So 1 AC switch need 4 diodes. You have 9 AC switch. How many diodes do you need? 36. Do you like to use 36 diodes? No, huge. So this is basic idea. This is okay, but nobody want to use it because the conduction loss is too high. It's too high. Then what can we do? So now your advisor say, this is the advantage. Can you propose your idea? You say, yes, I can propose. Then your advisor say, tomorrow you will graduate. Do you like this? Yes. But how can you propose? You say, I have no idea. But some students go back, then they provide some idea. They say, I can use this circle. So if I go this way, here, right? Another way, here. So one, this direction, another this direction, right? So bi-directional. Then how many switch do you use? One IGBT, two IGBT. You need one more IGBT. But the original, when you turn on, you have two diode. But now, when you turn on, you have only one diode. So you can save 2 volt drop. So the conduction loss is less. So conduction loss is less because the IGBT has a small voltage drop. The diode has huge voltage drop. So the diode is 2 volt. The IGBT could be 1.2 volt. So you can see we use one diode and one IGBT. And why do we need this line? Anybody has any idea? We can go this way. We can go this way. Can we remove this line? Without this line, is it okay? You can see we can go this way, right? And then we can go this way. Why do we need this? Anybody has any idea? Can we remove this line? Yes or no? Can we remove this line? Because we have current go this way, we have current go this way, and then we can block this line. Why do we need this line? Anybody has any suggestion? So my question is like this. We can go this way. And we also can go this way. But we don't need it this time. We don't need it this time. Is it okay? We use this circuit to replace this one. Is it okay? So you can see, we can go this way, or we can go this way, right? It is okay, but why do we need this time? No, any idea? Why people design this line? If it is useless, we can save money. We just remove it. Then we need less process. Then we create better reliability. Because one line can cause one problem. So why do we need this line? So anybody has any idea? If you have IGBT, you need to trigger the IGBT. So you have to put gating signal here, right? If you have gating signal, you have to get a ground reference, right? Otherwise, you have no reference. If you have no reference, how can you get the IGBT, right? So you have to get a reference here. So maybe here I need a reference. So I need a resistance to say this is ground and then this is 5 volt. For here, you also need reference. So your reference will be here. So you need a reference. So both sides need reference, so you have to type here. So this is your reference to getting the signal. So we need this line for reference. So it is a practical issue. Without reference, you cannot put voltage. So we also can go this way. Call it here and go here. So we call this is common emitter, because emitter common. And for previous one, we have this one and this one. This is emitter, this emitter. So this is common collector. Do you like common emitter or common collector? Which one is better? If you need a gating signal, do you take emitter as reference or collector as reference? If you have a gating signal, so which one is your reference? Your gating signal. You have to take this one or this one. Should be this one, right? So you should do common emitter or common collector. Common emitter. So you can see this is not good. So this is better. People use common emitter. So emitter, common. So if I need to get this one, I put 5 volt here. If I need to get this one, I put 5 volt here. So we call this is common emitter. So both devices arranged with emitter connect. So emitter connect. Both devices can be gate. So we can get to put 5 volt here. Then we can use isolated power supply, 5 volt power supply here. So this is your ground, this is 5 volt. This is your ground, this is 5 volt. So we can design isolated power supply. So this switch needs one power supply. This switch needs another power supply. Can we use one power supply for this one and this one? No, they need independent, right? So you cannot use power supply for this one and the same power supply for this one. Then you have a big trouble because they should isolate. Can control direction. So if we get in the IGBT, we can control the current go this way or the current go this way with each switch. So it is useful for most circuit. So in general, people buy this device, not common collector. People use common emitter circuit. So this is better. So because some companies say, I want to design matrix converter. So I need a device. I need an AC switch. Can you sell AC switch to me? Then the power device company say, no, I cannot sell you. But I want to buy. Then finally, the device company say, yes, I will design AC switch for you. So then they can put this one and this one become one switch. We call one module. So after you use it, then the power device company say, I can design packaging for AC device. So we can put 2 switch in one package, like this. 1, 2 switch in one package. So we call this bidirectional switch in one package. So in this package, we have 2 IGBTs and 2 IGBT and 2 diodes. So it is equal to 1 AC switch. And there is one company, Dynex Semiconductor. They are available to sell you AC switch, 200 ampere. So you can buy it. You can buy it. So this is good news. And another company say, I can show you the output leg. What is output leg? The output leg is here, one leg. One leg include how many switch? 3, right? 1, 2, 3. 3 AC switch in one module. So here is one module. 3 AC switch in one package. So a matrix output leg in one package. So it includes 3 AC switch. So it includes 6 IGBT. 6 IGBT. So totally for a matrix converter, how many packages should you use? 1 module, 2 module, 3 module, 3 module. Because you have 3 output line, right? 3 module. So you can buy 3 module, then you can design a matrix converter. So this is designed by Rockwell and Danfoss. So I think this is Europe company, Rockwell and Danfoss. And another company said, I can design 9 switch in one module. One module include everything, 9 switch. So this is the best. Single package, a complete matrix converter. So then become very small. Suitable for low power level. So Europe Power Electronics, EU-PEC, now have 400 volt, 7.5 kilowatt matrix converter. The name is economic, means cheap, economic module. One module, everything. Being used by Siemens. So Siemens use this kind of module to design the matrix converter available, so you can buy it. So you can see there are several companies, they sell you bidirectional AC switch. Then you can easily design it. So it is good news. You don't need to design by yourself. So you can see this is one AC switch in one package, so like this. So 1, 2. So in one module you have 2 diode, 2 IGBT, like this. And in general, we put common emitter. So this is Dynex 200 ampere bidirectional module. So you can see this is a ruler, so which means this is small size. So then totally how many switch do you use? This is one module. 1, 2, 3, 4, 5, 6, 7, 8, 9. You need 9 modules for 3-phase to 3-phase matrix converter. Then how about the current? 200 ampere, very huge. So you can see in one module, one AC switch. One AC switch is like this. So you need to buy 9 modules, then you can design the matrix converter. And here, this is output line. Output line. Each output line use one module. So one module, one module, one module. 3 modules, 3 packages for a 3x3 matrix converter. Used for medium converters, say 50 ampere to 400 ampere. So you need 1, 2, 3 package. So this is very good. So we use one module for everything. So 35 ampere, Europe Power Electronics company for one module, then 9 switch. So one package for 3x3 matrix converter used for small converters. We can say near 50 ampere like this. So you can see the inside is like this. Okay? So now they take away everything. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Total 18 IGBT, right? So in one module. So 3 by 3, 7.5 kilowatt, 400 supply. So you only need to buy one module. So this company is EU Power Electronics, EU Pack. So you can easily buy it. So it is cheap for 9 AC switch. So now we have a big problem. How can we change the current? Because this is one line. So sometimes I have to switch from A to B. If I switch from A to B, A is not turned off, but B already turned on, then short circuit. If A already turned off, but B not turned on yet, then open circuit, right? So we cannot open circuit, we cannot short circuit, but it is impossible, right? Because the switch is not immediately. If I switch too slow, then short circuit. If I switch too quick, then open circuit. So we cannot avoid these two rules. We cannot short circuit, we cannot open circuit, but we always do this. So what can you do? So you have to do commutation, current commutation. So how can you do this? So this could be your PhD dissertation. How can I avoid short circuit and open circuit? How can I do this? So this is a new issue for matrix converter. It is not an issue for inverter, but now it is an issue for matrix converter. So how can we do this? So your advisor SU, please propose your idea. Do not short circuit. If you short circuit, then the device will be damaged. Do not open circuit. If both of them open circuit, then you have 10 ampere here. The 10 ampere has no path. Then LDIDT will create a spike, damage these two switches. So what can you do? You say, I need to go sleep. So I have no idea, right? So you have to think. So now we want to explain. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 switch. So we say this is SAA, means this is input. Small a is output. We say this is SBA, B is input, A is output. We say this is SCA, C is input, A is output. So we use different symbol. Then we want to discuss what can we do. So we have AC switch here, we have AC switch here. If we turn on together, then short circuit. If we turn off this one and turn off this one, then open circuit. So what can we do? So we have to do current commutation. The output current commutation method rely on measure the output current direction. So we need to know output current go which way. Input voltage computation, we rely on measurement of the input voltage. We can use resonance technique, but this is too complicated. We don't want to discuss here. So we can measure the output current or input voltage. So two methods. So now here, the first one, that time current commutation. So we have SA1 here, SA2 here. So SA1, SA2 turn off, this turn off, this turn off. And then we wait 1 microsecond. Then we turn on SP1 and SP2. So we call this is what? Dead time, right? If we overlap, then this not turn off yet, this already turned on, then what happened? Short circuit. So we have to delay, wait 1 microsecond. We make sure this switch already turned off. And the way we wait 1 microsecond and turn on this switch, then we will be safe. But what is the disadvantage? Then during this time interval, this already turned off, this not turned on yet. So we create a spike, right? So we need some circuit to observe the spike, just like snap. So we will discuss later. So we use daytime. But daytime is not good. So people propose another way. So one student, he is very smart. He go back to sleep, and after 1 month, he said, I can propose 4-step current commutation. Then he received PhD. Then he published IEEE paper. Then he get a job. Do you admire him? Yes, he is smart. So now we want to discuss, how can we do this? So 4-step. So we have this sequence. So SA1 here, SA1 turn off here. So SA1 turn off here. And then SA2 is still on. So you can see SA1 turn off, but SA2 is on. So we can go this way. So we can go this way. And then SP1 and SP2 are turned off. Is turned off. So SA1 turned off, but SA2 is turned off here. Here you can say SA2 is turned on, but SP2 also turned on. SA2 turned on, but SP2 also turned on. If you turn on this switch and I turn on this switch, is it okay? You have a switch. If I turn on this switch and I turn on this switch together, is it okay? Okay, no problem. They share the current, right? So now you can see SA2 is turned on. But when SA2 is turned on, I turn on the SP2. So SA2 and SP2 both are turned on. Then what happens? If this is 10 ampere, then it is your 5 ampere here, 5 ampere here. So both turn on. And then SA2 turn off. But the SP2 still turn on. Is it okay? Yes. Then the 10 ampere go SP2, right? Okay, so 10 ampere go SP2. So SP2 still turn on. And then SP2 turn on, but SP1 also turn on. Because this go this way, this go this way. If this is turned on, can I turn on this one? Yes. Because the current will decide. If current is go this way, then SP2 is turned on, but SP1 turn on is useless. But I can turn on it, right? So you can see this one. If SP2 turn on, SP2 turn on, then we have a current path. SP2 turn on, then we have a current path this way. And then I turn on SP1. I turn on SP1. I turn on SP1. but the current is go this way. I turn on this one, but useless. But I can turn on it, right? So you can say, then if I have SA2, I turn on SP2. So then I still call it that. And after that, the current go this way, then the SP2 turn off, and then I can turn off SA2. So we have 1 step, 2 step, 3 step, then we change from A to B. So original is A turn on, this one turn on. Finally become B turn on. But I use 1, 2, 1, 2, 3, 4. I use 4 steps to finish. Then I can reduce the voltage stress and the current stress. Because when I turn on both, they share. Then the current becomes 5 ampere. Then I can reduce the load. So if you have a person run here, and then the second person run here, then the first person go here, and then the second person will get his duty. They have to touch and then give his bar to the second one, right? They have to overlap. So now we have to overlap. If we overlap, then it becomes more smooth. So if this one just threw his bar to him, then they might lose. So they have to run together, and smoothly he gave the bar to him, and he replaced his load to run later. So it is like this. So they overlap, but then we share to the second one. So the student proposed 4-step current commutation, and it is very useful. It is very useful. So what do we need? We need extra hardware. We require knowledge of output current direction. So we have to know the current go this way or go this way, go this way or this way. So we have to learn output current direction. We have to increase in gate drive complexity. So come here, very complex complexity to allow independent control of the device. And the control logic like this. And then we can reduce device loss because they overlap. So original we change from 10 ampere to 0, but then we have 10 ampere to 5 ampere and 5 ampere to 0. We reduce 50% of switch commutation. We call this is soft commutation. So the student proposed 4-step commutation strategy. They can be applied for bidirectional switch current flow. No action required when output current change direction. So it is shown here. We call 4-step commutation method. So what is 4-step? They say first, this is closed, this is open. Then because current go this way, then I know this is useless because the current go this way, right? So this is this way. So I can open this one because the current go this way. So we can make sure current go this way. So this is second step. And then we have current go this way. Then I can turn on this one because this is go this way. This go this way, this go this way. They can share half, right? So 5 ampere, 5 ampere. Then after that, I say you can turn off. Originally you turn on. Now you can turn off. I will replace you. So 10 ampere will go here, right? If 10 ampere go here, then we make sure current go this way. Then I can turn on this one because turn on this one is okay because current always share from SP2. So this is similar to this one. First, I take 100% responsibility. Then I close to you, we share 50%, 50%. Then I break, and then you take 100%. So it is 4 steps. So we can use this idea. So first one, we go here, then we say the current is this way. So this is useful, we go this way. This is useless, so you can have a break. Then we know current go this way, so we share 50%, 50%. Then you want to disconnect, you want to connect, then the second one, take the responsibility of the current. So you can open here, then you share 10 ampere. And if you share 10 ampere, your current go this way, then this can turn on. So we have 4 steps. So this is the 4-step strategy. So this is published in IEEE, and it is very useful. And finally, people say, in fact, we don't need 4 steps. We only need 3 steps. Why do we say we can reduce 1 step? Because the device turn-on delay is shorter than turn-off delay. So turn-on delay is 0.1 microsecond. Turn-off delay is 0.4 microsecond. So turn-on is shorter, right? Turn-on is shorter. So the meter delay can therefore be reduced. So we can reduce 1 delay because the turn-on is quick than turn-off. So we can reduce 1 stage. Then we can overall have 3 steps. So 1 step, 2nd step, 3 steps. So we reduce the middle step. You can see here. 4 steps. 1, 2, 3, 4. But turn on is quick than turn off. So if turn on is quicker than turn on, then they automatically create this step. Then we can reduce 1 step. Okay, so we can revise 3 steps. Okay, 3 steps. So you can see this is 3-step current waveform. So if you say, oh, I need 6 microseconds commutation from A phase to B phase, then the waveform like this. If you redesign, say, the commutation time only 2 microseconds, then it becomes this. So which one is better? 2 microseconds. But 2 microseconds is more dangerous. If you fail, then you broke your device. This is very safe, but the waveform is not good because it's too long. So you can see the difference. So this is the technology for matrix converter. We need a very short commutation time. But if your commutation time is very short, then which means they only overlap very short, then the bar will be dropped in the ground. So it is dangerous, right? So this is the result. Okay. If you can have overlap time, communication time, 0.1 microsecond, very, very short, then it is optimum. So very close to sinusoid. So we call this is technology. If you make your communication time shorter and shorter, your waveform become better and better, but you become more dangerous, right? Because you could be failed. So this is a result. So we can see communication time is very important for matrix converter. So we can use the current sensor to detect the output current. What can we use? Output is low. We can use Hall effect transducer to detect the output load current. We also can use a resistor to detect the direction of the load. We can use back-to-back diode. So then we know which diode is turned on. then we know the current direction. So if the diode is turned on, then we say, oh, this is called out. If another diode is turned on, then it is called back. We also can use internal switch current detection. We can use some IC, use this IC to detect the current. So now we can see some company develop some pattern. So here, they want to detect the current, output current. How can they detect? If we say, oh, this is positive, which is this is positive. If this is positive, then they go this way. So how about V1? And how about V2? So we can see if IL is larger than 0, then we go this way, Okay, so S1 and D1 turn on. So S1 and D1 turn on. S2 and D2 turn off. Okay, this turn off. How about V1? So we have go this way. So we have an IGBT voltage drop 2.5. This is 2.5. And we have this one, and this one is 1.2. The diode drop. This is plus, this is minus. But this is ground, which means D2 is minus 1.2. But the V1 is 2.5. IGBT 2.5. Diode 1.2. But ground is here. So plus minus, this is plus. This is plus minus, but minus is ground. So this is minus 1.2, right? So if you detect V1 2.5, V2 minus 1.2, do you know which current flow? Yes, you know it is called this way, right? We can see this one. If IL go this one, then V1, how about this one? This turn on 1.2. This is 1, this is 1.2. And go this way. So this is plus minus. So we can see V1 is minus 1.2, right? So you can see if V1 is 2.5, V2 is minus 1.2, then current go this way. If V1 is minus 1.2, V2 is 2.5, then go this way. If you measure the voltage, can you know the current? Yes. So this is one way. So you can put this in integrated circuit. Then they will show you which one the way, the current flow way. So we use device current to make current computation decision. So we direct measurement the current we can put on Hall sensor here. The current information can tell you go this way, okay, go this way. And then we also can measure the conduction voltage of the V1 and V2. If V1 is 2.5, V2 is minus 1.2, then current is positive. If V1 is minus 1.2, V2 is 2.5, then go this way, it is minus. So then we can use this to decide which switch should turn on, which switch should turn off. So some company develop this IC, and then you can set the current sensor. So they just measure the voltage. So you can see the current detection. So if we have a current go this way, it is 0. So 0 we don't know turn on or turn off. But if the current increase to 0.6 milliampere, then we know the current is turned on. So very sensitive, 0.6. So if the current go down, then in 0.6 we say it is turned on. But after it reaches to 0, then we can know this is turned off. So we can detect the current precisely. So the range is 0.6 milliampere. So it is quite sensitive and reliable, then we can use the current sensor to know the current direction. Then one company, they are very smart. They say, oh, I can design one IC. So I use the information, the IC information, to tell you when should you turn on, when should you turn off. So we detect the current and we teach you how to do the gating. And I put everything in smart IC. So you don't need to design your own circuit. I show you the integrated circuit, right? So you can see we can have current detection. Then from the current positive or negative, we can tell you which gate should turn on. Okay, so we have signal from previous gate driver. We have signal from DSP. We have signal to next gate driver. Then we tell you which one should turn on, which one should turn off. And everything is in IC. So this is very smart idea. So if you do this, then you can get a PhD. So some experimental results. So we have 2 kHz switching, 30 Hz output. So you can see this is the output current, 40 ampere. The current is like this. So do you think that this is sinusoidal waveform? Yes. How about the voltage? So the voltage is like this. So what is your DC voltage? DC voltage is here, right? So this is 1 pu. How about this one? 0.867, right? 0.867. Because now we do not have capacitor. Our voltage could be changed from here to here. But if you want to do modulation, you cannot consider this one. This is the best one. You have to consider the worst case. So you say my voltage is here. So 0.867. So this is the reason we say AC to AC, the peak value is only 0.867. We only consider this mode. And then you can see this is quite similar to rectifier. So now we do not use capacitor, so our voltage is not pure DC, right? Our voltage is like this. So this is the voltage, output voltage. And we have input voltage commutation. We can measure the input voltage to decide the current commutation. So we know the information of the input voltage. So if A phase is the peak value, then we know the switch A should turn on. And we require accurate and balanced measurement of the input voltage sensor. So we need an input voltage sensor. Then we can consider about the diode. What kind diode should turn on? When it is the peak value. So we have 4-step voltage commutation. Then we can avoid the mistake. So we can measure the input voltage to decide which one should turn on, which one should turn off. So you can see this one, 4-step, and here, and then we know it should be turn on here. So we turn on here, and here. If we turn on here, then we can automatically turn on here because it is useless. Then after that, then we can turn on here, and we can turn on here, then they share 50%, 50%. And after that, we turn off this one and make this turn off. So we have 1, 2, 3, 4. How many steps? 4 steps. Original, this turn on. Finally, this turn on, right? And how many steps? 1, 2, 3, 4. Change from this one to this one, 4 step. So we call this is 4-step commutation.